Thank you. Thank you for inviting me. And thanks for being here. All right. So I'm excited to talk to here because I think I've been working on this prediction problem, but from the 3D human motor control or like the pose perspective. And I think a lot of the people here might be a little bit more on the trajectory based approaches, but I think there's hopefully a lot of things that are common. So my work starts on this premise that we live in a world that is 3D and dynamic. It's full of life with humans and animals interacting with each other and its environment. And so a lot of my work is about reconstructing humans from single images in everyday photos using deep learning based approaches or from video. And once you start doing this, of course, you can't ignore the aspect of motion dynamics. And by here, dynamics, I mean it very loosely, not like the actual physical dynamics, but the way people move in the scene, motion, kinematics, the way people move. Okay. And so the really nice thing is, if you have a video, it allows you to predict what is in the future. And so we've been using this kind of insight since we started training 3D human reconstruction on video to predict what likely people are going to do in the next frame. So given an image of the person, you can see the predict in the before and the after what the likely pose was. Okay, we started this in a very rudimentary fashion where we had this video. Okay, so here are results from different viewpoints. And we're doing this from an image, not from a 3D input. And so we have this framework where we can predict the 3D humans from video. And what we did was this approach, reads out 3D humans from this center yellow representation. To do the prediction, you can actually take a single frame, train this model to hallucinate the features at the next future time step, which allows you to predict the plus one and minus one people, or like plus delta people. And so this was like a very simple way that we started exploring if you can predict people from images, people's motion from images. And then after this, we proposed, auto-regressive framework for this because it's motion. Given an input video, you would like to predict motion of the people in this 3D pose space, like so. And this was auto-regressive approach, and that you have this input image, you extract some features, and you can learn to, and then from these features, you can read out what people's poses are. And what you do is you just do this auto-regressive thing in the latent space by trying to predict the new future, you feed that in again, and then you repeat this process, and always you can read out the people's poses from this. Okay. And then, you can train this with various losses that are, common in 3D human reconstruction. Okay, so at test time, you can do this kind of prediction. And given that input video, you predict the future. Now, again, this doesn't actually have any 3D input. A lot of the existing works on 3D human motion prediction or synthesis starts out from 3D human seed. In this case, it was images. And this is because images actually contain some aspects of the task. So that was one of the reasons that we wanted to do it in images. And here are some results on natural or like images that we got from the internet. But this is a really hard problem. I think it worked in this particular sequence because the data set that we worked on was very characteristics. Like it was this like UPenn action data set. So there's a lot of sport movement, as you can see, like pitching. And so you can kind of, the motion is quite deterministic and ballistic, which reduces the uncertainty. And so, we kind of got some interesting directions that it got signals that you can do this from images, but it's a really difficult problem. And generating long 3D motion is really hard. So here is a paper that I like, which actually never got accepted for some reason, which is a transformer-based model for predicting 3D human motion. But you can see that previous approaches, like that are based on RNNs, get into these failure modes, like, static pose, non-moving motion, or, got stuck. And this approach was able to kind of keep on generating the motion, but really restricted to periodic motion. And so it's very difficult. And like, why is it really hard? It's a sequence to sequence problem, right? Like we have all of these toolkits, so why can't we just apply this? And so here are some of my thoughts on why this is a very challenging problem. So first, complex non-periodic human motion is task dependent or goal dependent. And so you need some conditioning. And so to do this out in the vacuum, I think is a little bit too much, and then the use cases of these things are often task dependent, right? Maybe you're driving a car, you want to know where people are going to go. And so you want to predict people in the context of its environment. And so you do need some conditioning. But once you get into this domain, you get in the problem of the lack of data sets. Right. So existing data sets are very limited in the length of its motion. So post-track, which I believe that some of is based on, is still quite short. It's also super, super crowded. And so it's very difficult to obtain like a consistent track of a person, which means that, your sequences are short. Then it's difficult to learn about long motion models. U-bend action is also quite short. And AMAS is super long, but it's motion data only, and there's no task specification whatsoever. I guess you could use some attributes or something, but yeah, it exists in a vacuum and there's no images or any other conditioning. Okay, and then the last thing is that to do 3D human motion prediction, you need to output joint angles, and joint angles is a continuous representation that is very difficult to regress to, and naively applying transformer is not enough. And so these were kind of like the challenges that we were facing. And today I'm excited to talk about this new direction that helps us kind of re-see this problem in slightly different views that goes around the problem of data. So first of all, we are going multimodal because goal dependent, it would be really cool to do something in a real life scenario where people are interacting with the environment, but it's too difficult to obtain 3D humans and environments still in the granularity that where the 3D pose is important, like in everyday photographs or everyday videos indoors. So in this work, we're going to focus on music as the conditioning. It's still some conditioning. Okay, obviously the data isn't really there, so we collected this. We are presenting a new 3D data set. And then we show what the kind of devil is in the details in order to make a transformer work on this. We still treat it as a continuous, but that's to be left on future work. Okay, so this is the work learning to dance with AIST++ that we presented at this ICCV. And so the goal of this work is to give in some music and a seed motion to generate, that's a seed motion. And the goal is to generate a framework that can keep on, that can generate arbitrary long sequences, but this doesn't actually have the results. Oh, there you go, there you go. Okay, so that's the generated sequences. And our approach is able to generate long sequences that correlates with music that more than previous works. Okay, so if anybody is listening, dancing is a universal language, and so let me corrupt you from the morning with this baby shark dance music. And so everybody likes to dance, and people do this a lot. And how can we, so the goal here is how can we also learn, train and model to dance to music? Okay, and really the challenge is this lack of high quality dance motion data. And then we also need to kind of innovate in the option of direction of the model, because now we have this conditioning that is music. So for the data set, we first created a new 3D data set based on an existing database called AIST Dance Video. This is a really nice work from Japan, Japan, I think, where they had 9 views, 9 cameras, and took a video of dancers dancing. And this is quite diverse. It's kind of, they do a lot of different genre of dancing. It's in a research science license, and it has a lot of videos, and it has 9 views. It's also instruction. It's kind of it's instructional based in a sense that same dancers dance to the same music, and so it has this uncertainty aspects of it's not like a single music is paired to a single dance, but this approach, this data set is really nice, but it wasn't 3D. It's all 2D. It's 9 views, but they're not calibrated. So basically, we went ahead. Rui Long, who is the first author on this paper, developed this framework to kind of put everything together in the current best practices of the things that we can do to estimate the 2D key points in the camera, triangulate the poses, do bundle adjustment over time, and then fit this simple human body model so that we can recover 3D joint angles and everything. And we've also open sourced this processing code, and he processed this thing, processed all of AIST, and we are releasing this data set as the AIST++. Okay, and then the AIST++ data set has calibrated cameras and 2D to 3D key points, and has motions in joint angle parameters as well as 3D joints. So hopefully this is useful to your research. And as you can see, it has a kind of wide variety of dance motions from ballet to like hip hop. And it is it also has 30 subjects, which is nice. For other reasons, other tasks also, but it also has a reasonable number of sequences. It's still not the largest thing ever, but it's reasonable. It's not small. Like in previous approaches in the dancing musics were like really small and specific. Okay, so yes, contains with 3D motion that is paired with music. And it has a lot of views and images and subjects and human 3.6M, which might be your familiar data set. Okay, so this is available at this link, so hopefully people can play around with it. Okay, now onto the model. The problem statement of this work is to generate long motion condition on music. So how do we do this? So during training, we have an input motion and input music. So we need some kind of a seed in this one. And then we output the motion. That's how it's being trained. And you want to output more than one, like you want to output conditional one. At test time, we run this model, but only take the first predicted one. And then we shift this over. And then we repeat this in a sliding window fashion to generate a long sequence. Okay, and our architecture is transformer based. And so input motion and the input music goes through its own transformer, which becomes another representation that is the same. And then we can concatenate this along, we can just put this in a big set and then send it to a cross-modal transformer, which outputs the human motion. Okay, so this seems easy enough, and in the output motion, you have this supervision. So this is simple enough, but the devil is in the details. And naively applying it in a GPT style really does not work. So the vanilla approach that the previous paper has tried is this GPT style autoregressive prediction. You have an attention that is masked attention, and then you predict, and at every single node predicts the next future. Okay, and this is how it's done in the language world. But this really didn't work for us. This would get stuck very quickly, and it will give you jittery motions. What works really is a full attention-based model. So GPT style is masked attention. So you only get to look at the new input gets to look at everything else, but the past ones are frozen and don't get to see the future. That's precisely because their objective is to predict the immediate next future. And so if you got to see it, then it's not a problem. So you can't really have full conditioning and have this objective for the GPT style model. But what works is that make everything into a full attention model. So it's basically a full attention encoder. And the output is not the immediate next one from each node, but the next K sequences or N sequences from the input. Okay. And this was, this is also very important. So here are some of the details. So that if you do this vanilla GPT, it really does not very good. And here are some of the metrics I'll describe later. So if you do full attention, but only predict the N+1 sequence, it's also not very good. But if you start predicting 10 things in the future, then the model really needs to pay attention to the past information and also the music, and this gives us the best result. Okay, and the one thing is that in GPT, you can't, in NLP, the window sizes tend to be very, very large. And this is like yet another reason why it's very inefficient to do a full attention-based encoding, because you don't want to re-encode like 1,000 tokens every single time you generate something new. It's really necessary for efficiency. But in human motion, you don't really need to have such long conditioning windows. Maybe it's like, 20 or 64 at max. And so you can easily actually do this full attention, and this is how it's actually implemented anyway. And so this really allows all the nodes to talk to each other, and this really helps generate very long lasting video music. So let's just look at qualitative results. So here again, so here it's already started. The causal, this is causal attention shift by one is the GPT model. And it gets stuck really quickly, and it just stops moving, as we saw in other work. If you do full attention, it keeps on moving, but it kind of looks weird. And if you do full attention, but predicted 20 in future, then it really gives you more coherent motion that is long. Okay, so that's like number one thing, the attention mechanism. And then the second important thing is also like early or late fusion. When you have multiple modes, when do you fuse? Late fusion would be you have a very deep individual transformers, individual embedding on each of these representations, and you do like a shallow embedding. But the early fusion is very important. And if you do early fusion, so the x-axis is like the nodes, right? So the first 10 say are like the motion seed, and the rest is the music attention, which is longer than the motion. If you do late fusion, it's really not looking at the music, and it can actually generate motion just looking at its past motion. But if you do early motion, it really starts seeing it. And so this was another small details that's very important to make it music. So basically, if you do late fusion, it basically doesn't pay attention to the music. Because it actually pays attention to the music, we can actually do something where you give in the same seed motion, but different music, and it generates a different dance. So this is music 1. And that's the music B, but these are two different sequences. They share exactly the same seed motion. So if the model was not paying attention to music, they would have generated the same dance, but it generates very different motions. Okay, so here are some comparison to prior work. DanceNet is RNN based, and the Lee et al. One is also a GPT based simple transformers. And we tried our best to re-implement these approaches, and we thank these authors for helping us a lot on this. Okay, so these are approaches that were 3D, but we also compared with 2D based approaches, but trained them with points. And you can see that other approaches don't really generate, generate something, but yeah. And these are deterministic methods. The deterministic methods fail ours is also deterministic, but it has seed motion, seed music, so that if the music is different, it's able to generate different motions. But in this AISC data set, the same audio can have multiple corresponding motions. So if it's a deterministic model directly from the audio, it gets stuck. Okay. All right. So for evaluation, we added there exists some of the metrics in this world, but we added more metrics because metrics are always important, and it's difficult to define for this kind of tasks. So the first is an alignment with music, and so shown in orange is the music beat. by looking at discontinuities in the music. And we want to make sure that this aligns with the kinematic discontinuities. And the interesting thing is that it's not that every single time music has a beat, you actually have to move to it. So it's not bi-directional, but like anytime there's like a kinematic beat, you would hope that there's kind of music beat to it. And then we also introduced a motion distribution matching, similar to FID, but not using the inception network, but using classical motion feature algorithms, motion features, and we compute, we compare their distributions for realism. And we also measure diversity to make sure that it's not just memorizing a single moment. And obviously for these tasks, user study is very important. And so we conducted one where we compare ours with the others. So with real data, so real data is much better. So this is the challenging one, and ours win like 25% of the times. But compared to other method, ours is significantly wins over the other ones. And the question is this a realistic dance? And we also tried to ask participants who have some dance experience. All right, so here are some more results. Okay, all right. So we are, this is a challenging problem, and previous approach is really not able to generate nice motions. And so I think our frame, the details really matters, and doing those things properly helps the model. But there are some limitations still, which is a way that it really likes to generate repetitive motion. I think this kind of goes in the level of task specification. I think we need a little bit more way to control this. It's still a deterministic model, although it takes in the seed motion. So you can change the music to generate different dance, or you can also keep the same music, but use different seed motion to generate different. And we would like to improve this in future work. It would be also really nice to model contact and physics, like in the recent ways people are doing, like works like humor, and other multimodal input conditioning, like other than music, maybe more choreography based approaches, which requires a lot more detailed data. There is a nice work at SIGGRAPH that does this, but it also has much more supervision on the data. So recovering those things unsupervised in an unsupervised manner would be really nice. I would like to end here. Thank you.
Perfect. Thank you very much. So very, very interesting and nice talk, Angjoo. It was great. Let's see if there is any question from the audience. Or I can always go first. Hamid, you want to say something?
No, I will be second.
Okay. Okay, yes. I saw you unmuted. That's why I paused. Yes, so very interesting results and findings. One quick maybe question, because I may have missed it. So you are all of these visualizations in the simple space?
Yes. I didn't really talk about this. And so, yes. So the nice thing about the simple is that simple is a linear blend skinning model, meaning it outputs the joint angles. And so yes, if you have the joint angles, it's really easy to transfer that and to retarget it to new characters. So they are like that representation kind of looks like that, that thing. But then like once you have that thing, you can easily transfer it to different characters. And so this is a very important point, actually. If you're predicting only 3D joints, it's much harder to transfer because joints are, you have to solve the inverse kinematics once you start joints, right? You want joint angles because joint doesn't express all of these things. And so, yeah, so these are basically represented in that representation, but like once you have it, you can put it in this character, and this character is from Adobe. I am
Nice.
sleeping on this, but there's like a nice data set, nice sets of characters that you can get the name of this. Mixamo, yeah.
Yeah, thank you. This is great. Yeah, Simple is, I think it's a great contribution to the field, and many works are dependent on it right now. One thing that I had always in mind was, so I agree with you. A simple space is way better than the joint space if you want to do any type of prediction or movement, like transferring the movements. One thing is when you're training models, so this simple space makes the model not to be end-to-end, right? I mean, it's from one space to the other. Is it going to be any by end-to-end, I mean in the image space or like the actual 3D space, if you have 3D data, then because it goes from simple to simple, right? The transfers, and then you reconstruct.
Yeah. So this work goes from 3D input, right? You have like 3D simple like seed motion, and then you predict it. But it's easy to actually connect it directly to images, actually, because going from images to 3D is also an end-to-end approach. And so, like, for example, in this work, we actually did like input is video, but then the prediction is 3D. And then we do this by like the video becomes 3D, and then like, in the latent space, it kind of ends up outputting 3D. So technically you could be doing this from images, but in this one, yeah, we're not using the image data for the dance.
Thank you. We have one question from the audience. I wonder, so Fabio's asking, yes, I wonder how this works when you transfer your music conditioning to an actual task. It seems music may be providing a larger amount of supervision, for example, frame-wise supervision, while task may just be a label.
Yeah, I think this is an interesting point, but what I envision, I think, is that, I mean, I kind of think about it in like interacting with people in everyday everyday scenarios. And I think getting like a single label of the task is also difficult, right? I mean, it's not always the right way to specify it. Okay, let me just say like this. If it was a single label, I think it would still work because I think it's much easier. Actually, music is very subtle correlation, right? Because like I said, one of the failure mode of this approach is that when you train this model, it basically just learns to ignore the music first, because this is like a motion generation task, right? Like if the dancing is kind of repetitive, you can just look at the motion and kind of keep on repeating it. And you don't need to pay attention to the music. And actually the model prefers to do this kind of things. So music is actually, it's good. You're right. It's dense, but it's also very weak correlation, as opposed to a task, I think, would be very strong. And so that's one thing. But also two, I think the task will also be generated in this kind of continuous formulation. Like, for example, if you're trying to, maybe there is a goal, right? Something like go and pick up cut a cucumber or something like this. But then you also have to consider your environment and all of these things, which kind of come continuously. So maybe that's, that's another idea. But thanks for the question. It's a good question.
Absolutely. Hamid, do you want to go next if you have any questions?
First of all, nice to meet you, Angjoo. I haven't had a chance to personally meet you when I was in Bay Area. I'm not longer in Bay Area. I'm far from that. I'm in the other part of the world, Australia. So great talk. Hopefully we can meet each other in one of the conferences, upcoming, hopefully physical conferences. Great talks. I have just a question again. It's some of the the question Fabio had was similar to what I wanted to ask. Is what's the contribution, which you are already answered. Contribution really you believe is from motion, and how much contribution is from music, from what is generated, which I believe you answered it. Another thing, do you believe that what is generated is really new? It's a model do extrapolation, or is it simply interpolation of the what is seen in the data? And that's back to the metric as well. I would like to ask a couple of questions on that.
Yeah, I mean, I think this is pretty much interpolation. I mean, I think extrapolation is hard. And so this is why we see a lot of repetitive motion. Like, I guess it's not like we do some nearest neighbor based kind of lookup, I think. And it's, I think it's, yeah, actually Relong, the first author, I think is in the audience. So please, jump in or write something if you have other thoughts about this. But I think it's kind of like motion graph, like kind of interpolation. Yeah, that's, I think it's similar.
And in the metric, I believe you are trying to, one of them try to say how diverse is what is generated. Assuming you compare it against the previous work, which could be potentially also not diverse. I'm interested if you have a baseline, for example, a part of real data, which is not used and just used for the diversity comparison with the what is means.
Yeah.
It means a part of that to just say, okay, if I see a couple of new dances, how diverse would be, and what is my generator, how far is from that?
Yeah, very important. Yeah, exactly. That's a number over here, actually, which is like the ground truth diversity number is this thing. So like higher is better. There's no real units here, but like high, right? And so it is quite diverse in this. And in this sense, ours is like medium. But for example, this work is very diverse. But then if you look at the results, it's like this is the middle one where, let me just mute the music.
Okay, I got it.
Yeah,
definitely. It's not realistic then.
It's diverse, but not realistic. Exactly. So diversity is an important metric, and this is why we have like some baselines or like some what the ground truth data is. You also want to make it to like you want to also make it quality too.
Great work. Thank you.
Thank you.
Thank you. Actually, there was one other question which seems to be interesting. So Goida is saying that thank you for presenting your interesting work. Great talk. What does it happen if you suddenly change the style of the music? For instance, if you concatenate two different soundtracks, how does it affect the motion?
This is a really good question. I don't think we did this, but we did this thing where like we have this like same motion, starting motion to one music, right? Because at test time, how we actually do this is take the ground truth seed and then the ground truth pair like of the test sequence, and then run that too. But we also take random seed from every like training sets, right? And so the seed and the motion often don't align. So it's kind of like you're dancing in a way, but suddenly the music changed. So that's kind of like always what the setup is. And then the model always changes the dance to match the music. Okay, Relong is here. Maybe we did do this like concatenation one.
Yeah, that's a good question actually. Yeah, we did try once to like switch the audio in the middle of testing, and it turns out it quickly like switch the dance motion to like match the new music style, like within 2 seconds, 1 second to 2 seconds something. So yeah, it switched roughly quickly. So yeah.
Yeah, it's I think similar to the same seed different dance situation, which is like kind of you're dancing in one way but then quickly really does it, which is nice because it really does pay attention to the music. And for a long time Relong got this model to produce nice motion but then wasn't paying attention to music. It was one of our issues. And so this early fusion actually makes a big difference, and it's a small thing but it's very important.